Hello, my name is Lukas Nölke, and this talk is on how to compute minimum cost k-hop Steiner trees in tree-like matrices. It is joint work with Martin Böhm, Ruben Hüksma, Nicole Mego, and Bertrand Simon. Let's define the problem in a more informal setting first. So consider the following situation. You have a company whose headquarters are in Bremen, and you have some customers in Oslo, Berlin, Prague, Lyon, Barcelona, and Madrid, where you want to deliver some goods to. Now, in the classical Steiner tree problem, you search for a transportation network of minimum cost that connects your headquarters to each of these cities. So this would be, in this case, a minimum cost Steiner tree. However, in practice, you may have additional constraints, and you may, for instance, want to first go from your company's headquarters to some regional distribution hub, and only then to the customers. So for instance, from Bremen, we would go to Oslo directly, but we would go first to Berlin, have here our regional distribution hub, and then to Prague. And we would go from Bremen to Toulouse for our regional distribution hub in France, and from there deliver goods to customers in Lyon, Barcelona, and Madrid. So this would be then, since we are having two hops from our headquarters, first to the regional distribution hub and then to the customers, a two-hop Steiner tree. And of course, you can think of many more applications. For instance, this could also be instead a communication network, where you want to route some traffic through this network. And again, you want to minimize the cost of this network. But at the same time, by bounding the hop distance, you want to increase the reliability and reduce transmission delays. We will abbreviate this problem by k-hop MST, where the Czech letter sh is used to distinguish MST in minimum spanning tree. Let me now define this problem formally. So as an input, we've given a finite metric space, which is a set of nodes V and a distance function D. And we're also given a set of terminals and a root R. And of course, we're given an integer k, which is our hop constraint. Then we want to compute a Steiner tree S with node set VS and an edge set ES, which has a root R, so that it spans all terminals and so that the depth of it is at most k. And we want to find such a tree such that the edge cost is minimum. So we sum over all edges and sum the cost and minimize this quantity. Now, we've already seen one special case where k equals 2, which is in fact the uncapacitated facility location problem. Some other special cases include the k-hop minimum spanning tree problem, where all nodes are terminals, and the Steiner tree problem, where k is at least n. And of course, then from these special cases, known hardness results carry over, which also lead to the following in approximability result. For non-metric graphs, Alfandari and Pashos showed that there cannot be a 1 minus epsilon times log n approximation unless problems in NP can be solved in time n to the O of log n. And there's also matching upper bound when k is constant from Kortsas and Pelek, and they give a O of n to the epsilon approximation when k is part of the input. For metric graphs, we have approximation results of O of log n for k of MST by Althaus et al. And we also have a 1.52 times 9 to the k minus 2 approximation for k of MST by Cantor and Pelek. We have also lower bound results due to Maniem and Stallman, saying that no constant factor approximation can be achieved, even with unit weight edges, unless p equals np. And also due to Alfandari and Pashos, there cannot be a p-test even for 2 of MST, unless p equals np. However, for the Euclidean space, there is a q p-test known when k is constant, and when we are on the plane, this yields a p-test. In contrast to these approximation results, we give exact algorithms for specifically structured metrics. That is, for metrics that are induced by a path, we can obtain an exact solution in time O of k times n to the 5. And for metrics of Treewidth omega, we can obtain a solution in time n to the O of k times omega. Then using a recent result due to Feldman, Funk, Könemann, and Post, we can extend this to bounded higher dimension metrics and show that we can obtain a solution of cost 1 plus epsilon times the cost of an optimal solution that uses one hop less than we do in quasi-polynomial time. This talk focuses on the first two results, but let me give you a brief idea what bounded higher dimension metrics are. So, as the name already suggests, they model transportation networks. And if you look at this picture here for an intuitive example, here is Bremen in the middle. And if we want to go from Bremen somewhere far away, for instance to Hamburg, then we would take a highway in order to travel via shortest path and pass one of these few hubs. And this is a property that holds in metrics of bounded highway dimensions on multiple scales, making them a really useful and practical class of metrics. Let us now consider matrices that are induced by paths. So our nodes are numbers from 1 to n, and let's say they're ordered here from the left to the right. And we also assume that all of the nodes are terminals. We can do that because if we have a node such as this one that is not a terminal, we simply take the next node to the side of it where we have more edges, so in this case to the right, and we contract this edge, and this way we have a new Steiner tree that uses at most as many hops and also doesn't have a larger cost. Now, a key observation that we will use in our approach for the path metric is the following. So first we denote the depth of a vertex in the Steiner tree by L of v. And now in this situation we have three vertices S, I, and J, with S being in the middle of I and J and of a lower depth than I. And I here is attached to S. Then in these situations and in an optimal k-hop minimum Steiner tree, J would never be attached to I, neither directly nor via some path, because you could also instead attach J directly to S, and this would have a lower cost and also less hops. So then the idea is to recurse on the left and the right of S. But of course, there may not be a left and a right of S, so we have to put a little bit more work in. And let's talk about how to do that. For this, we use a dynamic program. And a cell of this dynamic program indexed by P, S, A, and B saves the minimum cost of a p-hop Steiner tree that has a root at S and that covers all nodes within the interval AB. And from our observation before, we can assume that S will not be part of this interval. Now here you see an example of this where P equals 3 and the vertices between B and S are left out from this tree, but everything between A and B is covered. For dynamic program, we have the following base cases. First, of course, is if A is greater than B, then our interval is empty and we don't have anything to attach, so the cost is 0. If A equals B, then we just have a single node, and this will be attached directly to S, so our cost is the distance between S and this node. And the last base case is when P equals 1, so we only have one hop to give, so every node in the interval AB has to be attached directly to the node S, and we have to sum these costs. For the recursion, look at the following picture. It depicts an optimal solution for our dynamic programming cell. So we have a Steiner tree rooted at S, and here S prime is the child of S that is closest to it. And then we have a subtree that on the right of S prime, which goes from S prime plus 1 to B, and on the left of S prime, which goes from C to S prime minus 1. And then we have possibly several remaining subtrees from A to C minus 1, which are anchored directly to S. Then the cost of this tree is the distance from S to S prime, this edge, plus the cost of the subtrees, which have a hop distance of P minus 1 and are anchored as S prime, plus the cost of the remaining subtrees, which are anchored at S and have hop distance P still, and span the interval from A to C minus 1. To find the correct values of S prime and C, we take this minimum over all S prime and AB, and then over all C in the interval between A and S prime minus 1. Taking then up to n guesses for each of these, we get a runtime of n squared here for one cell. And since there are k times n cubed many programming cells, we get a total runtime of k times n to the 5. And the complete solution can be computed by querying the cells of the dynamic program that contain the cost of the left and right subtree of the root with hop distance k. This concludes the proof of the path metrics. Let's consider next metrics that are induced by a tree. So since we now talk about Steiner trees, in matrices that are induced by a tree that may look entirely different from the Steiner tree, we introduce some additional notation to avoid some confusion. So whenever I talk about a tree or a subtree from now on, I will refer with that to the tree that induces the underlying metric. And when talking about Steiner trees, we will talk in terms of labelings and anchorings. And we say a node U has label L of U and mean by this the depth of U in the Steiner tree. We also say a node U has the anchor alpha of U and mean by this the parent of U in the Steiner tree. And of course, since not all vertices have to be included in the Steiner tree, if this is the case, then the label will be infinity and the anchor will be the vertex itself, and no other vertex can be anchored to it. So here we have an example. We have the root R and a Steiner vertex U, and then terminals U1 to U3. And we see R has a label of 0, U is anchored to R and has a label of 1, and the UI have anchor U and label 2. And when the labeling and anchoring such as here are consistent, that is for every vertex U, the label of its anchor is exactly by 1 lower than its own label. And then we speak of a labeling anchoring pair, or short LAP. Now this may seem a bit redundant because whenever we are just given an anchoring, we may ensure that this condition holds for a labeling and thereby produce a unique labeling from an anchoring, simply by starting at the root, which has a label 0, and then considering the next vertices that are anchored to the root, giving them the label 1, and so on. However, does this also work for the other direction? And the answer is, it depends. Well, if we're talking about a Steiner tree that is optimal, that has minimum cost, and where the shortest paths are unique, then we can also produce again an anchoring from a labeling simply by connecting a vertex U to the closest node that has a label of 1 less than U. And we can in fact assume the shortest path to be unique by simply applying some small epsilon noise to the distances in the metric space. However, since we will again go for a recursive approach, we will not always have such a complete solution. And if we look at partial solutions like these, then we cannot simply recover an anchoring from a labeling or vice versa. So we need this redundant information. But now let's talk about how to create a dynamic program for this setting. So our partial solutions, what you may suspect from working on a tree metric and writing a dynamic program, will be on subtrees. That is, we want to compute a partial labeling anchoring pair on a subtree TV of some node V, and we want to extend this to the whole graph. But how to do this actually? And in fact, even if we have the simplest case of just a leaf, then it is really unclear how to connect this to the remaining graph because we have no information how the Steiner tree looks here at all. So we really need some additional information, and this is where we will use what we call anchoring guarantees. So remember from before where we connected U to the closest node with label of 1 lower. We need this kind of information for the labeling anchoring pair of the whole graph to be able to have some idea where this node V could be anchored to. And this is exactly what our anchoring guarantees provide. So we have, on the one hand, inner anchoring guarantees, phi I of V, which give the closest node to V of label I in the subtree rooted at V. So here, for instance, we see that phi 2 of V is V itself, and phi 1 of V is this node here, which V is anchored to in the Steiner tree. And we also allow these anchoring guarantees to take a default value, which then indicates that there is no such node to anchor the vertex V2. Further, we have outer anchoring guarantees, rho I of V, which then just describe the roughly closest node to V of label I in the remaining graph. So here we have that the root is rho 0 of V, which is of course always the case. And here are rho 1 and rho 2 of V. Now here are two important observations that we should keep in mind in the following. So first, the situation that V is its own inner anchoring guarantee for some label. This is actually a characterization of when a vertex belongs to the Steiner tree hash. So a vertex only belongs to the Steiner tree if there exists a unique label IV such that V is equal to the inner anchoring guarantee of this label. And since the anchoring guarantees represent closest nodes to V of the given label, either inside or outside of the subtree, if the label of V is I plus 1, then it should be anchored to either the inner or the outer anchoring guarantee of label I. And this is then what our dynamic program is based on. And here we have a dynamic programming cell. It is indexed by the vertex V and also by its outer and inner anchoring guarantees for all possible labels. And it should contain the minimum cost of an LAP on the subtree such that the two following properties are satisfied. So first, the inner anchoring guarantee of label I should be the node of the subtree of label I that is closest to V. And for other vertices in the subtree that are contained in the Steiner tree, so which have depth not infinite, they should be anchored to either the outer anchoring guarantee that is of label 1 less than their own, or to a node of the subtree that is also label 1 less of their own. So intuitively, this should compute an optimal way how to extend a labeling anchoring pair on the graph outside of the subtree to a labeling anchoring pair on the whole graph while respecting these anchoring guarantees that we are given. Let's look at the base case again. So in this case, we have the leaves and we have always 3 cases. So the first case is that V is part of the Steiner tree, which is what this condition shows us by the previous observation. And then the IV also gives us already the label of V. So we know how to label it. And then the anchor of V should be the outer anchoring guarantee of label 1 lower. So the cost of this LAP is then the cost to connect V to the outer anchoring guarantee. The second case is that V is not part of the Steiner tree. And in this case, it cannot be a terminal, and there cannot be any inner anchoring guarantees that use V. So in this case, we have a cost of 0 because V simply is not connected. And then all remaining cases mean that some of the anchoring guarantees are inconsistent or some values don't add up. So we set the value of the programming cell then to be infinite. So this concludes the leaf case. Now let's look at the recursive formula. Here we look at a node V and its children in G, and the cost of the corresponding dynamic programming cell with given anchoring guarantees consists of the cost to anchor V, CV, so the cost of connecting V to its anchor, plus, and here we sum over all children of V, the cost of the respective programming cells for these children with some special anchoring guarantees, which we have to compute. And what is important here is that these anchoring guarantees for the children of V are consistent with the anchoring guarantees of V that we are given. And for the outer anchoring guarantee, this is in fact a unique choice, while for the inner anchoring guarantees, we have a set of consistent guarantees from which we choose one that minimizes the cost of the dynamic programming cell. Now, before we look at these in a bit more detail, let's note that since for the inner anchoring guarantees, we may choose from up to n values, and we have k different labels, we have a running time of n to the O of k. Now let me stress again that really the crucial and most important part of our dynamic program are these anchoring guarantees and how to propagate them through these calls of the DP. Next, we look at CV, the cost to anchor V, and essentially this is the same as the cost to anchor a leaf, which we looked at before. So we have the same 3 cases, and the only difference is that now we also have the option to anchor V to one of the inner anchoring guarantees of the appropriate label. So we choose the closest option between outer and inner anchoring guarantee. Let's now look at the anchoring guarantees of label I for the children Vj. So for the outer anchoring guarantee, we have 2 cases. First, if the inner anchoring guarantee of V is inside the subtree of TV, so somewhere here, for instance, then we pick our outer anchoring guarantee to be equal to that of V. This is because the shortest path outside of this tree will always lead through V, so we have the same closest nodes. Note that, however, we could have some node here that is outside of the subtree of Vj, and that is closer than this outer anchoring guarantee. But however, in this case, the inner anchoring guarantee, which is in the subtree, will always be still closer. So this is the one we would choose to connect Vj, and we do not have a contradiction. And in the second case, where the inner anchoring guarantee of V is outside of the subtree, so it could be here, for instance, then we have to choose between either the outer anchoring guarantee of V or the inner anchoring guarantee of V, and pick this for Vj. And finally, the inner anchoring guarantees are determined as follows. So if the inner anchoring guarantee of V is non-existent, then there also cannot be an inner anchoring guarantee for Vj, because otherwise V could already anchor to this. So in this case, we then do not give any anchoring guarantees for Vj as well. The second option, if the anchoring guarantee for V is inside of the subtree for Vj, then again, since the shortest path goes through Vj here, this also has to be the anchoring guarantee for Vj, and we only get this single choice for Vj. And in the last case, we get several different options. So when the inner anchoring guarantee of V is in a different subtree than that of Vj, then for Vj, we may actually choose first for Vj to be no anchoring guarantee, or for the inner anchoring guarantee to be some node in this subtree that does not contradict the anchoring guarantee of V. So for this not to contradict, it has to be at a larger distance from V than its own inner anchoring guarantee. And this is then how we compute these anchoring guarantees, which is the crucial part of our dynamic program. To compute a final solution, we simply query the dynamic programming cells of the children of the root. And for the subtrees, we allow for all possible inner anchoring guarantees within the subtrees. But for outer anchoring guarantees, we only allow to anchor at the root at label 0, since anchoring to other subtrees would be more expensive than connecting directly to R anyway. This concludes the discussion of the tree case. Let's now briefly look at the case of metrics of bounded tree width. The main difference lies in the following. So for the tree, we looked at subtrees and we wanted to extend LAPs from the whole graph to these subtrees. And doing so, we had only one entry point into a subtree, which was the node V, which spans the subtree. Now, when we have matrices of tree width omega, instead of one entry point, we will have roughly omega entry points, which correspond to bags of the tree decomposition. And then again, we want to extend the LAP from some subgraph CB to the whole graph and use that there are only few entry points. And now instead of just one anchoring guarantee for vertex V, we need anchoring guarantees for all of these entry points. To give a bit more detail, a tree decomposition is a tree whose nodes B correspond to bags SB, which are subsets of nodes of our original graph, which contain at most omega plus 1 vertices. And then if we have an edge of our original graph, then both endpoints of this edge must be contained in some bag of the tree decomposition. Further, if we look at all bags in the tree decomposition that contain some fixed vertex of our original graph, then these bags form a connected component and TD. And we do not just use any tree decomposition, but we use a nice tree decomposition, which gives us some additional structure on the relation between parent and children bags in the tree decomposition, which we will crucially use in our dynamic program. And as I said earlier, in the dynamic program, we want to extend an LAP on CB, and the CB actually contains vertices that are in descendant bags of some bag SB, which would be our entry points into the subgraph. Then the idea of the dynamic program is similar to that of the trees, except that we index the cells by bag, and we have inner and outer anchoring guarantees for every node U that is inside such a bag. And then in our recursive formula, we target the structure of the nice tree decomposition to propagate the anchoring guarantees consistently. This, however, requires quite some effort and technical detail, which is beyond the scope for this presentation. So to conclude, while previous results only consider approximation algorithms and inapproximability, we give exact solutions on well-structured metrics. We also give a quasi-polynomial time approximation scheme that uses one additional hop as recurse augmentations on metrics of bounded high-Y dimension, which is extremely relevant for practical applications. Some open questions are whether or not the dependency on k in the running time can be dropped to improve the running time or to show matching lower bounds.